Folks, now we're going to swing back into this chapter 16, resuming back to 16.6 in the formation of complex ions. So we took that little deviation into chapter 22 just so that we could understand complex ions and coordination compounds in a little bit more detail. But now we're going to get back into the equilibrium stuff. Okay, so we've played with these reactions already, kind of near the beginning of the semester, right? In that intro to qual experiment. And when we deal with the formation of complex ions, this is an equilibrium situation, as you can tell. And so all of our same, let's write that down, same equilibrium stuff applies. So meaning Le Chatelier's principle applies. All of the stuff that we talked about, like Rice tables, calculating equilibrium concentrations, all that applies here. Okay. So for example, if we look at the formation constant, we've got a new letter to put next to our K, Kf. Okay. This describes the formation of a complex ion. And so what that means is we want to see the complex ion as a product when we're dealing with Kf. Okay. And as it turns out, most Kf's are very, very large. So in other words, much, much greater than 1. And you can see that when we put this together, right, we've got the, now that you know how to name this, right, this is tetramine copper 2. Okay, so you can see the tetramine copper 2 complex ion forms from 1 copper and 4 ammonias. And, right, so we've got to raise that ammonia to the 4th power. But you can see here this value, it's huge, okay? And so again, this is why Lewis bases do a really good job of sequestering metals, because if we think about this now, our equilibrium position will be way far to the right, and we don't expect to have a whole lot of free copper ions in solution in the presence of ammonia, because it's going to make this complex ion with great efficiency. Okay. So we can also come up with the dissociation constant, Kd. And as I'll just show right away, Kf equals 1 over Kd. So for this one, it says calculate the value of Kd for the above reaction. Well, they're the opposite of each other. Okay, so if Kf is really large, that means Kd is going to be really small. So I could write Kd is 1 over Kf. And I can calculate that over here, right? That's going to be 1 divided by 5 times 10 to the 13. So 1 divided by 5e13. And of course, it's a really small number. So Kd means 2 times 10 to the minus 14. And if we wrote a reaction for this, it would just be the opposite reaction here, where now my complex ion is dissociating into the free copper and 4 ammonias. And now, once again, because we recognize for this reaction, Kd is much, much less than 1, that means the equilibrium position is way on the left, and that effectively means the same thing as this Kf value being much, much larger. So in other words, when we have, for this specific reaction, copper and ammonia present, they will very efficiently form the tetramine copper 2 ion. And we expect to not have much copper or ammonia in solution at all. Okay, so we're going to do a sample problem next in a part B video.